Hello and welcome. In the next video he'll be building a convolutional neural network to remove the noise from the images. And our goal here is to actually learn the basics of using Keras API with computer vision problems and also TensorBoard. TensorBoard is a TensorFlow tool that allows us to see how are we doing when it comes to training. It allows us to visualize the progress of the training. So keep in mind that here we don't focus on the specifics of how autoencoders work or convolutional neural networks for that matter. Our goal here is to learn the basics of Keras API and the practical sides of how to work with some kind of a specific computer vision problem. And we will also see how we can use a dataset that are included in Keras. We'll work with Denoise dataset. This is where we have a dataset of numbers written by hand with labels, and we'll use the dataset to add the noise to them and then train our network to remove this noise from those images. And we will also go through the process of building a convolutional neural network, and again we won't go into details because we don't have time to do that, but we'll cover the basics of how to do that in Keras. And we will also talk about how to train your network and also how to plot the training progress. And actually we'll start with the last 2 points because those are the most practical steps. Once you have the code ready, you need to train your network and understand the process. So let's open the terminal, and we have 2 terminal tabs here. And one of the first thing that you have to do to actually visualize the progress of the training is actually to run TensorBoard. And to run TensorBoard, you have to just type in TensorBoard with the parameter log there. And this parameter is just the path where the TensorBoard should look for the files that contains information about our training progress. See that this directory is actually, we put this directory inside our Keras code. So it will actually, during the training, it will put those informations into this directory, and the TensorBoard will actually be able to read those informations. So this is the first thing that we want to do. Just type in TensorBoard --log there equals to, and in our case this is /tmp/tb, and then we will see the information that the TensorBoard server that will allows us to see the visualization of our training programs is available at this address. And this is simply a localhost address, so we can just copy and paste that. So let's copy and paste that and just run it. In this case we run it in Chrome. And since I've already trained my network, I can see charts of 2 very important values, and this is our loss value, this is our training loss value, and that simply means that as our network is being trained, our loss value should go down, it should decrease. And we also have additional parameter that will allows us going in the right direction, because when you're training your network on one data set, it will naturally, the more you train it, the more it can actually remember some of the parts of the data set. And to make sure that that won't happen, because we don't want to have a network that will remember stuff, we want to have a network that will deduce more or less intelligently what's going on. So we want to have another step of verification here, and this is where val_loss comes in. Val_loss will verify on totally different data set if we are actually getting better at reducing the loss. So in general, as our loss function, the first one goes down, and also the second value loss goes down. As long as those 2 values goes down, it means that we are going in the right direction. So as you train along, you will see the progress of it inside the TensorBoard. Here you have to just from time to time refresh the page. So let's have a look at the sample output of the training session. So here I've saved the actual output of the training session, and this is simply I've went to the section 1's source directory and type in python 3 train.py. And train.py, this is our main script for training in this section. And remember that you want to use the version of the Python that we installed using Miniconda. So in my case, this is python 3 command. And why not run this script right now? Well, because it takes a bit of time to actually finish, so that's why I'm showing you the output only. So this is the output that you've seen in the TensorBoard, and the first thing to notice is that once you run this script, you'll see the information that we are using TensorFlow backend, and you've seen this information once when we were testing our installation. Then after that, got the information about how many samples, how many distinctive elements in our dataset we are using for training. So here we have our MNIST dataset. It has 60,000 samples, and we will also have information about how much data we are validating during the training. And this is 60,000 samples. We are using it for each training session, and then after that we validating on totally different 10,000 samples. And what you will actually see next is that how much those training sessions, which we call epochs, are we actually using. Inside the code we are using just 2 training sessions, and this is for most computer vision problems, even the simple ones as we have here. This is far too few. Usually you want to use like 100 epochs or something like that, and the idea behind that is that you have to experiment, did a lot of trial and error to see what amount of epochs is actually good, so that our loss function, the value of our loss function on our training set and also during the validation will decrease, right? So this is a lot of training and error to figuring that out, how much epochs do you actually need to make that happen. And here we've chosen just 2 epochs to make things simple. So here in first epoch we've got this information about our loss function in our training set, and as we can see from the epoch 1 to epoch 2, the value of this loss for our training set is getting smaller. And also when it comes to validation, it's also getting smaller, so it means that we are going in the right direction. The question is, how much epochs do we need to actually get the lowest values for both training set and also for our validation set. But as I said before, this is more about testing a lot of different possibilities, doing a lot of trial and error to actually figure that out. So this is how these training sessions actually look like, and I highly encourage you to run the script and see it for yourself, and also look at the TensorBoard during the session to see how it will actually update. And in a moment we'll go into the code and we'll see how we can change the number of epochs to use so you can train it with more epochs. And one more thing to keep in mind is that the values in the TensorBoard actually updates after each epoch, right? So once you get started with epoch 1, and you'll see the progress bar here, you won't see any data at the beginning in the TensorBoard, right? But after first epoch you'll see first value, and then after second epoch it has to finish to actually update the TensorBoard. So this is one of the things to keep in mind. Okay, so now it's time to actually dig into the code, because this is our main objective here. So let's look at train.py script, and we'll start with just importing the necessary parts from Keras. And one of the main objects that we'll be using in this code is sequential. And sequential is kind of a container for our neural network or deep neural network. And then after that we are importing the layers that we'll be using in our model. And of course there are different type of layers, and as I said before, we won't go into the details about each layer, what it actually means. Those are 2 main objects that we'll be using from Keras to actually build our model. And then of course we also need to get the data, and we are getting the standard dataset from Keras. Keras contains a lot of dataset that we can use out of the box, but we need to modify our dataset, we need to add noise to it, so that's why we are putting everything inside different kind of a script. But I will talk about dataset in a moment. We also want to import the callback that we'll be using to actually update the information about the progress of the training, and this is where we need to import TensorBoard object from Keras callbacks. And once we import all the necessary parts, it's time to build our model. And keep in mind, especially when you're a beginner, you are eager to understand how it all works, how those models works, and it takes some time to actually understand what's going on, and here we won't actually do that. But keep in mind that we're starting with sequential, and we're just creating a empty container for our neural network, and we adding different layers one after each other and with different parameters basically. And one of the things that you have to keep in mind, especially when you're getting started, is the input underscore shape parameter for the first layer, and this will specify what kind of data can this first layer accept, and this is also will tell you what kind of data do you have, shape your data so it can be used with this layer, it can be trained on this layer. And here we have images which is basically 28 by 28 pixels in size, and we have black and white pictures, so we have just one channel. And this is our Denoise dataset. It has been prepared in that way, it has been converted in the right way, so we don't have to worry about it because it has been already prepared in that way. And later in this course we'll actually go through examples of how we can prepare our own data. Right now just keep in mind that it's very important to know what kind of data our network is actually accepting, and then make sure that our data that we are using for training and also validation is actually the right data, it has the right shape. So once we've configured all the layers, we stack them up, the next step is to actually compile this model. Actually we will compile it into a TensorFlow model, and we need two parameters to do that, to compile our model. The first one is optimizer. Out there different optimizers good for different kind of problems, and throughout this course you will see that we can use, we'll be using a variety of optimizers. And you usually will pick up just you will know the type of optimizer that is best for a certain problem, because this is, usually when you have a model that works, someone tested it, it will also include some tips about what kind of optimizer to use for best results. In our case here we are using Ada Delta optimizer, and that seems to work. Then one of the very important also parameters when we compiling the model is our loss function, and here it will basically tell us how we can actually optimize, how we can reduce the loss. And here we are choosing binary cross entropy, which is pretty standard for this type of problem, and we can basically just use that. The next step is to actually, our model is ready, and then we can just get the data, and we will actually need two sets of data. First data that we need is the actual training data from Keras, from our Denoise dataset, and also for each image of a digit we also need a Denoise version of it. And also, apart from the training data, we also want to get the taste data. So the training data set, remember, we've got this information that we are using 60,000 samples to actually train our data, and we are using 10,000 samples for validation. So those 60,000 samples are from x_trained, so our data set, test data set, is totally different and has those 10,000 that we've got the information about. And we will talk about getting the data in a moment. And then the last step is to actually train our data. And we are using, as our input, we are use our noisy data, and as our output we are using our the actual images, digits without noise. So this is how our network is actually learning. As you remember from the schema of the example deep neural network, in the input we have one image, and at the output we can have another image. And of course, during the training, our network will figure out those features that are specific to certain numbers, and will figure out those features and actually learn them, so it can recognize those numbers from the, even if there's a noise inside the images. Then the next parameters is number of epochs. By default we've chosen 2, so we can save some time, so we can just quickly see how it works. But even though with just 2 epochs, it takes a little bit of time to actually train this model, and to get a real result you have to choose this number into actually 100 or something about. And remember, we train those models until we have both the value of val and the value of val underscore loss. Those two values has to go down, and if any of those values goes up, it's no longer decreasing, it means that our model can't be optimized any further. So we always look for those breaking points when some of those values actually goes up. Then the next parameters is bar size, and this is simply how much data should be put into just one epoch. And try different values to see if you can get different results. Here 128 seems to work pretty well. Then after that we have shuffle parameter, and this simply means that without shuffle every epoch, I believe, you get the data in the same order, and in some cases this is not optimal. And with shuffle, on every epoch you have totally different data is being changed. The sequence of data is actually randomly changed. So for some computer vision problems this actually works really well, where you have this additional kind of a randomness in a way that you inject the data into the network. Then a very important part is validation underscore data, and this is where we put our validation data set, and here we are just using our test set. So those two parameters are exactly the same. The idea behind them are exactly the same as we are using with fit. So our first, this is our input, right? And here we are using totally different data set. Our test set is totally separated from our training set, and those are noisy versions of our data set. And then we have the actual numbers without noise as a second parameter. So remember, in both cases, when we are providing the data for fit and also for validation data, we are just passing the two set of lists basically. In one list we have the input data, in the second list we have the expected output data, and this is how network is looking for mapping between those two, or changing its own parameters so it can match those two. Then the last parameter is basically just the callback that will allows us to see the progress of our training, and this is where we are using TensorBoard object. And remember that we have log underscore dir parameter here, which is the path that we are using to put the information about the progress of our training. And this is the same parameter that we need to use in TensorBoard command, so it can, we can use the same source of information in both cases, so we can synchronize between those two and see the actual progress. And there are a bunch of parameters for TensorBoard here, but those are pretty redundant ones. So one thing that we have to also explain is how to get the actual data set. So let's look at another script that we have inside the source directory, which is noisy digits. And if you want to see the data set, the visuals of data set, you have to install matplotlib. Using conda install matplotlib equals 2.2.3. This is the version that actually works with this script. And let's run this script so you can see the actual data sets first. So it's Python 3 and digits. And here we'll see first the original data set. So this is our Denoise data set. Those are the images that we are using for training. And this is the version of this data set with added noise. So we can see that we have plenty of noise here, right? And one of the things that we have to also keep in mind that this dataset is actually converted, each image is converted to actually a matrix, right? You have to keep that in mind because it keeps coming up with different computer vision problems. Let's look at the code again. So here what we have is actually we are generating our noisy.mnist datasets using getNoisy.mnist. And in this function, first we are getting the data that has been prepared in Keras. You can use from Keras. This comes from MNIST dataset, and this is you can import that from Keras datasets. There are also different datasets, a lot of computer vision datasets. We'll be using those different datasets later on. And when we run MNIST load data, it will basically just return our training dataset with labels. So in the first part we have the actual images that has been converted into the matrices or the lists with just numbers, and the labels that will say, you know, which image or which list represents which number. Because as we remember, MNIST is the mapping between this dataset is about figuring out what's on the actual image, what kind of numbers on actually image. And we also get the test dataset in the same way, and getting the actually converted images to matrices and the labels for those images. And I won't go into details about how we actually add the noise to those images, but just keep in mind that this is all operations on matrices using NumPy, and we are using a couple of very standard NumPy commands to do that, and basically just adding a bunch of numbers in the right way to our images, and then converting back matrices into the shape that we need to have to actually use them for our network, right? So basically what we are doing here is that we're getting the already prepared data set from Keras that has been converted into a matrices of specific shape, which is 28 by 28 with just one channel, and we just adding the noise to it, which basically means adding a specific set of numbers into those matrices and just return them. So this is what we are doing here. And of course, to see those, we are using matplotlib, using plot.mnist to actually show those results. I hope that this video was useful. In the next video, we'll summarize this section. So until then, take care, and I'll see you in the next video.